Hi, my name is Nate Moracle, and today I'll be presenting our work titled Accelerating Unstructured Mesh Point Location with Ray Tracing Cores. This work was done in collaboration with Inga Wald, Will Usher, and Valerio Pascucci. First, I think it's worth explaining what exactly a point location query is and why they're useful. So given a query point in space and a collection of elements, a point location query returns the element containing the query point. Sometimes these queries are also called point containment queries, or more simply just point queries. For visualization, we often use these point queries for direct volume rendering, by casting an array through our data, querying containing elements at regular intervals, and compositing the colors of these elements from front to back. But you might also use these point queries for particle advection, where you want to have a particle flow through some vector field. Or you might use them for range queries, where you want to know if one point is within the range of another. For voxels on a regular grid, point queries are actually relatively straightforward, as the coordinates of the voxel containing your query point can be found by taking the floor of your query point position. However, unstructured datasets pose challenges to point location queries, as elements have unpredictable shapes and sizes, so this flooring trick doesn't work anymore. Instead, elements must be located using an acceleration structure. We can test if our query point is within one of the internal node bounds, and if so, we traverse that node's children. And then at the leaf, we can use a point and element containment test to determine which element contains our point. In this work, we explore a mix of element types, specifically tetrahedra, pyramids, wedges, and hexahedra. These elements are composed of both triangle and quad faces, where the quad faces can curve to form a curved bilinear patch. Because of this additional complexity, unstructured mesh point location is much more challenging than point location in a regular grid. It's difficult to quickly build these acceleration structures while also maintaining high-quality trees. And then once you have those structures, traversing through them on a GPU tends to introduce many expensive and divergent memory accesses. From there, determining if a point is contained within a particular element usually involves some sort of root finding method. The key insight to our work is observing that there are many similarities between these point location queries and the ray tracing queries supported in hardware on modern GPUs. The ray tracing cores in Nvidia GPUs handle both acceleration structure traversal as well as right triangle intersection testing. Additionally, construction of these GPU acceleration structures is done for you using real-time construction routines. Similar to point location queries, a ray query traverses through an acceleration structure, testing for intersection with primitives. But one of the big differences is that array has both an origin as well as a direction, while the point query only has an origin. While a point is simply contained within the boxes and primitives, rays can be thought of as a continuous set of points along a line that are both contained and intersected by boxes and primitives. So the theory is, if we can transform our queries into ray tracing problems, even if that transformation introduces complexity, we can leverage ray tracing hardware as a result, and therefore we might be able to improve overall performance. So to evaluate this theory, we implemented 5 different methods, starting with a pure software reference. Each subsequent method we will improve on the previous and move more work to these ray tracing cores. For a reference method, we build the bounding volume hierarchy over our elements on the CPU. This BVH is then uploaded to the GPU for accessing CUDA. To perform our point location test, we traverse down the BVH as described before, rejecting subtrees that don't contain the 3D position and performing point and element tests at the leaves. Although this reference is relatively fast, it suffers from complex acceleration structure construction and traversal code that make it really inaccessible. So for our second method, we can build a hardware-accelerated BVH over our primitives as if we were intending to do a ray query against the custom primitive type. And then next, we can make our point query fit what the ray tracing cores expect by interpreting the query point as a ray, but a zero-length ray. So in theory, traversing a ray will automatically traverse any point along that ray, which includes the origin. For the direction, we just choose something random because we don't really care about that direction. Finally, we can write a custom intersection program that ignores the ray direction and instead interprets the ray origin as our query point for our point and element test. With this method, performance should improve because BVH traversal is now handled in hardware. And we also no longer have to maintain this complex BVH construction and traversal code. However, the ray tracing cores aren't really being used to their fullest here, as we're still relying on software to handle point and element testing. The software intersection code causes expensive context switches between hardware ray tracing cores and the programmable cores of our GPU, which limits our potential speedup. So for a third method, we can observe that if we were to trace a ray with some length to it, still originating from our sample location, we will always hit one of the containing element's faces. And if we assume for the moment that our elements consist only of flat faces, then those faces can be triangulated and then intersected using the built-in hardware ray triangle intersectors. So for this method, we tag each triangle with the ID of the corresponding element, which can be found using using the triangle ID returned by our array. Neighboring elements will generate overlapping triangles, and so we construct all triangles to face inward and enable backface culling to avoid intersecting neighboring elements. Now, one caveat with this backface culling method is that it's possible that we get false positives at the boundary of our volume. So to fix this edge case, we need to perform a final software point and element test on the returned element ID to verify our ray origin is actually inside the element it hit. Another caveat is that we're creating duplicate faces for all internal elements, which consumes memory and slows down ray traversal. For our fourth method, instead of duplicating shared faces and storing one element ID per triangle, instead we merge these duplicate faces and now store two element IDs per triangle. If we hit the backside of a triangle, we use the first element ID, and otherwise we use the second element ID. If a triangle isn't shared, we store -1 for the ID on the unused side. This reduces the number of triangles in our acceleration structure by 2 times, and now we no longer have these false positive intersections at the boundary, so we don't need to do that final point and element test in software anymore. Finally, we need to address the fact that some of our elements have curved bilinear patches. So far, our triangle-based methods only work for elements with planar faces and result in incorrect results for curved elements. So to extend our hardware-accelerated point queries to support these bilinear elements, we can make a couple of final observations. First, curved bilinear faces can't be easily triangulated. If we were to use 2 triangles, those 2 triangles would either lie below or above the patch, but they wouldn't exactly match the patch. To more accurately represent that patch, we could use more than 2 triangles, but then that would consume a lot of memory, especially for hexahedral meshes. We could also go back to using a software intersection program for quad faces, but this would likely be slower than our original software point and element tests for hexahedral meshes. Fortunately, bilinear surfaces satisfy the strong convex hull property, which guarantees that each bilinear surface is entirely contained within the convex hull of its control points. We can use this property to identify when a problematic point location case occurs, and then finally, the thing that we can recognize is that these convex hulls for these bilinear surfaces are tetrahedra. We already demonstrated that we can identify if a tetrahedron contains our query point. So for our 5th method, we extend our prior shared faces approach to account for these bilinear patches. For each curved bilinear patch, we generate 4 shared triangles instead of 2, such that those triangles form a bounding tetrahedron that contains the bilinear patch. Like before, those triangles store 2 element IDs to indicate which element each side points towards. But now we additionally mark the triangles belonging to these bilinear patches and orient the triangles for our bilinear patches to face outwards away from the bilinear patch. If our ray hits a backface to a triangle belonging to a bilinear patch, we perform a final ray bilinear patch intersection test in software to determine what element our query point is actually in. So with this last method, we only need to do a single bilinear patch intersection test, and only if we find our query point lies within a bounding tetrahedron to a bilinear patch. So to recap, we presented 5 methods, each method incrementing on the last, and each method offloading more and more work to the ray tracing cores. So in theory, the later methods introduce more algorithmic complexity, but then that complexity is done in hardware rather than software. To evaluate these approaches, we chose to use a relatively regular desktop, and to implement our different approaches, we used a mix of Optix 6 and CUDA. As far as GPUs go, we tested on a mix of hardware, both with and without ray tracing cores, some consumer cards, and then some workstation cards. We tested our different sampling methods on 5 different datasets of varying sizes, ranging from 3 million tets on the Fusion dataset up to 62 million tets on the sparse Japan earthquake dataset. For the Agulhas current, Cyvis pump, and Japan earthquake datasets, we also tested performance on their non-tetrahedralized versions, which consisted of 14.4 million wedges, 6.4 million hexes, and 8 million hexes, respectively. Finally, some of these datasets require that we interpolate scalar values on the vertices when we're sampling the element. And then other datasets have self-centered data, in which case we don't need to do this interpolation. First, we ran some memory tests to see how our method stacks up against the baseline. And I'm only going to highlight a couple of the key takeaways here, but this full paper is in the table if you'd like to check it out more. Major groups of rows are the reference method, the replicated faces method, and then our final shared faces method. For each method, we measure peak and final memory usage. First, we found that cards without ray tracing cores use more memory than those without ray tracing cores. I kind of suspect that this might be an issue with us using Optic 6, and we expect more similar numbers if we were to move to Optic 7. One thing that we discovered is that Optic 6 will quickly run out of memory if you try to build an acceleration structure over all primitives at once. So to work around this issue, we found that by splitting our unstructured mesh into many smaller meshes and building smaller acceleration structures over those before combining them all into one big acceleration structure, we could save up to 70% of our memory usage. Another thing that we found is that our memory usage grows larger and larger as we move to triangle-based methods. In the final method, we don't duplicate shared faces, but we still tessellate our element faces, which we found increases our memory usage over the baseline by about 2 to 3 times. Next, we tested the raw number of queries we could execute per second under some synthetic benchmarks. So these tables show how many point queries we can do per second for the different cards, methods, and datasets. Once again, I'm only going to go over some key observations here, but if you're interested in taking a closer look in this table, also check it out in the paper. So first, we found random sampling to be much worse than uniform sampling, and this suggests that ray tracing cores are still affected by work divergence. We'd likely see a similar result with regular grid point queries, so this isn't really that surprising. Next, we found that on our non-RT core hardware, we actually do about 2x worse for the tetrahedral meshes as we start leaning more and more towards ray tracing. And that also makes sense because ray tracing is more algorithmically intense than a point location query, and we're not getting any benefits here from hardware acceleration. However, if we do have hardware acceleration, then we see up to a 6.6x performance improvement for tetrahedral meshes and up to 11x speedup for hexahedral and wedged meshes. And at each method iteration, by offloading more and more work to ray tracing cores, we realize more and more performance improvements despite introducing additional algorithmic complexity. Next, we integrated our point location queries into a direct volume renderer for a better understanding of a more real-world use case. So the takeaway here is that our performance improvements from our synthetic benchmarks translate to real-world performance improvements, where with hardware-accelerated ray tracing, we see up to a 4x performance improvement in frame rate for tetrahedral meshes and up to a 15x performance improvement in frame rate for wedges and hexahedral meshes. So to answer our theory, hardware ray tracing frameworks can indeed be extended to support point location queries, and despite increasing the algorithmic complexity in the transformation, we are still able to realize significant performance improvements due to hardware acceleration. As far as future work goes, we believe that there's still a lot of work to be done in finding new ways to use ray tracing cores and frameworks to accelerate a broad range of problems. We believe that more generalized range queries, closest point queries, and KNN queries could all be accelerated as well. I believe that it's also worth considering these problems more algorithmically and holistically, as it's possible that even on GPUs without ray tracing cores, that faster BVH construction is still worth making this transformation, or that rays could somehow be less algorithmically complex than some alternative in software. I'd like to conclude by saying that if you have any ideas on what additional purposes you think these accelerated ray tracing frameworks could be extended for, please reach out. And I'd also like to thank Nvidia Corp for lending us some cards that we needed to do these evaluations for. Anyway, thanks for listening.